This video is a continuation of the TNB frame, where we developed how to find the unit tangent vector, the principal unit normal vector, the binormal vector, and the equation of the oscillating plane. So this video is an example of finding all four of those components for a particular space curve. We're going to use the vector valued function you see on the screen there. R of t equals e to the t, e to the negative t, t times the square root of 2. And proceed to find the unit tangent vector, the principal unit normal vector, the binormal vector, and the equation of the oscillating plane, all at the t value of 0. So if you wanted to know the point on the plane, you could find that by plugging the value of 0 in for t, and you'd have e to the 0, e to the negative 0, and 0 times the square root of 2, which would produce the position vector 1, 1, 0, which would start at the origin and point to the curve. Its terminal point would lie on the curve at the point 1, 1, 0. So that is where we're going to find all of these new components. To begin, we need to find the unit tangent vector, and by definition the unit tangent vector is r prime of t divided by the magnitude of r prime of t. So finding the derivative of r of t is the first step, which is not that difficult. I mean, the derivative of e to the t is e to the t. Great. The derivative of e to the negative t is negative e to the negative t, and the derivative of t times the square root of 2 is the square root of 2. So finding the derivative, not that difficult. Now we also need to find the magnitude of the derivative. So the magnitude will simply be the square root of the sum of the squared components. So it should look like that. Square root of e to the 2t plus e to the negative 2t plus 2. Therefore, t of t is the quotient of these two values, r prime of t divided by the magnitude of r prime of t, and it would look like this. Since we're interested in finding t of 0, we can plug 0 into this expression for t to find the specific unit tangent vector at the point in time when t equals 0. This is the general unit tangent vector. It will, or in other words, it is the unit tangent vector function. It will provide the equation of the unit tangent vector at any time t. We care about the specific time when t equals 0, so we'll replace all the t's with 0 to find t of 0. Let's move that up there, make sure you can see it. And so we have r prime of 0 over magnitude of r prime of 0. When you plug into r prime, you'd get 1 negative 1 square root of 2. When you plug it into the magnitude of r prime, we get 1 plus 2, the square root of that, which is very convenient. We get the square root of 4, which is 2. So notice that I've gone from using a vector in the numerator divided by a constant to writing it just as a single vector. This would mean that we have divided each component by this constant of 2. So we have 1 divided by 2, negative 1 divided by 2, and square root of 2 divided by 2 to produce this vector. Alternatively, you could put a 1/2 out front of the vector, and inside the vector have the expression 1 comma negative 1 comma square root 2. So that's t of 0, which is pretty straightforward, not too difficult. But we're going to progress now to finding n of 0. N of t was defined to be t prime of t divided by the magnitude of t prime of t. I cannot do anything with t of 0 to find n of 0. I must go back to my expression for t of t and find the derivative of this. And this is the point where I have to point out that it will take some time. Finding the derivative of this involves finding the derivatives of 3 separate components. And the component is not e to the t. The first component is e to the t divided by the square root of this expression. And the second component is not just what you see here for y, it's this thing divided by the square root expression. So you're going to need to use the quotient rule multiple times to find t prime of t, because we must find the derivative of the x component, the derivative of the y component, the derivative of the z component. So I have not taken the time to type up all the steps to finding that derivative. I suggest that you review how to use the quotient rule, how to use the chain rule, and make sure that you can reproduce this expression as well. So it turns out, interestingly enough, that all three of these components end up having the same denominator when we find their derivative. Therefore, I once again pulled that denominator out and just made it a group denominator, and this is what's left behind in each component x, y, and z. Just a quicker way to write it so that I don't have to write this multiple times. Now, the next step would normally be to find the magnitude of t prime of t, which, wow, that would take some intense algebra. But because we don't want to find the, I guess, general expression n of t, we only care about n of 0, we can actually go ahead and just plug in 0 to t prime of t, and then find the specific magnitude of that one specific vector. So we will not be producing an n of t function, we will go straight to n of 0. Now if you needed to find n of t at multiple different points in time, it might be worth your while to go ahead and find the magnitude here. But we're just going to go ahead and plug in 0 to t prime of t. So when you plug in 0, a lot of nice things happen, right? This becomes e to the 0, which is 1. This is e to the 0, which is also 1. And so you've got 2 plus 2, so the first piece right here is simply a 4. E to the negative 0 is 1. Hey, this is also a 4, so it's 4 comma 4. And then over here, you're going to have e to the 0 minus e to the 0, so 1 minus 1 is 0, so this component's 0. And so we'll have 4 comma 0. Plugging in 0 down here, you're going to get 1 plus 1 plus 2 is 4, so 4 to the 3 halves. And so t prime of 0 is 1 over 4 to the 3 halves times the vector 4, 4, 0. 4 to the 3 halves is the same thing as 4 to the 1 half, which is 2, cubed, which is 8. So this is really 1/8. 1 over 4 to the 3 halves is 1/8. So 4 over 8 is 1 half, 4 over 8 is 1 half, and 0 over 8 is 0. And so this is t prime of 0. I need n of 0. So n of 0 is t prime of 0 divided by the magnitude of t prime of 0. So I simply need to find the magnitude of this particular vector. Finding the magnitude there, it's the square root of the sum of the components squared. We end up with 1 over the square root of 2, or 2 to the negative 1 half. So n of 0 is t prime of 0 divided by the magnitude of t prime of 0. And if you simplify this, work through this, you would get the square root of 2 over 2, comma square root of 2 over 2, comma 0, and that's n of 0. So we've now found 2 of the necessary pieces. Our third piece is to find b of 0, which is the binormal vector at the point t equals 0. By definition, b of 0 is t of 0 crossed with n of 0. So I go back and find my expressions for t of 0 and my expression for n of 0, do the cross product, which I'm leaving up to you to fill in the blanks, but it should result in this vector right here, negative 1 half, positive 1 half, square root of 2 over 2. And that's 3 of the pieces. The only thing left to do is find the equation of the oscillating plane. In order to find the equation of any plane, you simply need a vector that is normal to the plane and a point on the plane. The point on the plane we know is r of 0, 1, 1, 0. A vector that is normal to this plane is b of 0, negative 1 half, positive 1 half, square root of 2 over 2. We know this is normal because the cross product of any two vectors is perpendicular to both of them. And since these two vectors lie in the plane, something that's perpendicular to two vectors that lie in the plane will also be perpendicular or normal to the plane. Therefore, this is a normal vector to the oscillating plane. Notice I said a normal vector. Therefore, we can use any normal vector to actually find the equation. Why not use one that's a little simpler? For instance, if I were to multiply this vector by 2, I would get -1, +1, square root 2, and that's an easier normal vector to work with. So if you recall, the dot product of your normal vector with a vector in the plane must be 0, because the orientation between these two vectors geometrically is a right angle. And when we dot two vectors who are at a right angle together, the dot product is always equal to 0. Now, where did this expression come from? This is taking the general point in the plane, x, y, z, and subtracting away from it our specific point, r of 0, 1, 1, 0. So x minus 1, y minus 1, z minus 0, dotting that with a normal vector, and move that back down there. If we do the dot product, we get this expression, and then if we distribute the negative symbol, get rid of the parentheses, combine like terms, we end up with -x plus y plus z squared roots of 2 equals 0. And this is the equation of the oscillating plane. So we found all 4 points, but I want to spend the last several moments of this video showing you geometrically that everything worked out as we hoped it would. So what I have graphed here is the original expression r of t, and this is the point 1, 1, 0. We first found the unit tangent vector, so I'm going to turn that on. There's the unit tangent vector. You can see that it is in the direction of motion, and it is 1 unit long. If you're wanting to use CalcPlot 3D to graph these yourself, when you put in the components of the vector by choosing a vector, you can pick whatever color you want it to be. You can make it wider or narrower, and then this is important, the initial point. It defaults to the origin, so if I did not put 1, 1, 0, which is the coordinates of this black point, this vector would have been over here, because it treats it as a position vector. But I want to do the vector that starts at this point, and so that's why I put its initial point right there. We can then also turn on the normal vector. This is the equation we found to be the normal vector. You'll see that it points into the curve, as it should, as we learned in the first video. And these two are at right angles to each other. Once again, I told it to start at the point 1, 1, 0. Then we found the binormal vector. I've turned it on, starting at 1, 1, 0. From this orientation, you can't see it because we're looking down in 2 dimensions, but if I rotate it a little, there we go. We can see that the unit binormal vector is perpendicular to both the tangent and the principal unit normal vectors. And that's the TNB frame. Lastly, I'm going to turn on the graph of the oscillating plane. We found the oscillating plane to be -x plus y plus z times the square root of 2 is equal to 0. Here's the graph of that, and you can see that the pink vector and the green vector both lie in that plane, and that the black vector is normal to it, as it should be, and this geometrically backs up everything we did and gives us evidence to believe that what we did is correct. Again, this isn't proof that we did all our steps right, but it sure is pretty compelling when I see the graphs of this is the unit tangent vector, this is the principal unit normal vector, this is the binormal vector, and we've got the equation of the oscillating plane, and they all fit together so well. So hopefully this will now help you try out a few of these problems on your own and walk through these steps. Thank you.